Okay, everybody, welcome to AI Makerspace's very first community-led public community session. We are so excited to bring you this 90-minute session where you're going to learn and you're going to build and you're going to hopefully ship something and share it by the end of this thing with two of our amazing LLM Ops Cohort 1 students who are here to teach you about reinforcement learning with human feedback. We've got Juan and Pano in the house. Juan is an experienced company builder, seller, very, very much an absolute killer on the product side. And you would be amazed at how deep technically he's been able to get, even just in the past few months that we've seen Juan really come up to speed on generative AI, on fine-tuning LLMs, and of course on reinforcement learning with human feedback here. So talk to him about companies that he's shipped in the past. He is a wealth of information and just really a true pleasure to have in our community. Pano Evangelou, calling in from Amsterdam today, really an emerging legend in our community, and a guy who's coming in from a non-traditional background, not traditionally trained in software, but has really kind of continued to make the leap over from more of a mechanically oriented, more atomistic view of the world. He has been really just an awesome guy. He's always up later than anybody else to join us on East Coast and West Coast time. We're really excited to be able to offer this community session in the middle of his day. And, you know, he really led this reinforcement learning with AI feedback idea into what ultimately became this reinforcement learning with human feedback community session today. So I am going to sort of get out of the way today and hand it off to these two guys who will be responsible for walking you through each and every step of the reinforcement learning with human feedback session for the rest of the day. So Juan, Pano, guys, off to you.
Thank you, Greg.
Yes.
Pano, you have
Greg.
the word.
Yeah. Give me a second. Share my screen. Great. So you can all see my screen. You can hear me. All good. So yes, hello everyone and welcome. I'm happy to welcome you as well to another of our Wednesday sessions with the awesome AI Makerspace community. Thank you, Craig, Ali, Chris, and Sarah for hosting us and letting Juan and me giving us this step to present. Everyone else, if you haven't followed them or you don't know them, follow them on LinkedIn and everywhere else humanly possible. So together with Juan, the legend, we will be breaking down reinforcement learning with human feedback, the what, how, when, and why. And we will be focusing and diving deep into the implementation of RLHF, from the general workflow to dissecting the different components, and finally to applying it to fine-tune LLMs. So of course, we will also be doing hands-on implementation. We will be sharing two notebooks, which are prepared with great care from Juan and super detailed. So let's start with the basics. What is RLHF? RLHF is a powerful reinforcement learning method that uses human feedback to overcome the challenges of traditional RL. Currently, RLHF is all focused on training large language models and align them with complex human values. This technique has never been more successfully applied than when OpenAI did to significantly improve the performance of ChatGPT. Let's quickly brush through the basic training stages of LLMs. So let's recap. First, we train the model using unsupervised learning on huge corpuses of the curated text, the big body of the beast, as you can see in the image. So this is the most resource demanding process. And at the end, we get the pre-trained model, with good performance at simple generation tasks. Step 2 is supervised fine-tuning, SFT. It's a more focused approach. It involves training a model with a labeled data set that maps inputs to desired outputs. At the end, we get a model with improved performance on desired tasks such as classification, generation, instruction following, etc.
Hey, Pano.
Yeah.
We're just seeing only a part of your shared screen where it looks like the top is lower and the bottom is cut off a little bit. I'm not sure.
Yeah,
Okay.
Pano, try hitting F11.
No, wait. Let me do it again. No, now everything is a mess. Let me go back into presenter mode and try once more. How about now?
Great.
Is it better? Okay. So step 2 is the supervised fine tuning, as we said, but still we're only our model is trained only with simple next token prediction objective, only predicting the next token, the next word. And now we're asking why use RLHF after this stage. So the real question is what makes a good text? And it's a hard question to answer because it's subjective and context dependent. And there are many applications that require creativity, truthfulness, or tasks like summarization and detoxification that cannot be judged only with the accuracy of the next word. Writing a loss function to include it is also, to include this metrics is also difficult. So imagine how can we measure if a model's output is funny? We don't have metrics for that. So what better if we use human feedback as a measure of performance, and to that end we will use methods from reinforcement learning to directly optimize a language model with human feedback. Just a parenthesis here. The question is why not keep fine-tuning, supervised fine-tuning instead of RLHF? I will focus only on the performance image here, and we can come back for the differences in data and tasks. We are going to see them in the notebooks. So you can see this is the comparison of performance on summarization tasks done by OpenAI. And you can notice that the human feedback outperforms not only the supervised fine-tuned model, but also the reference summaries. So in these tasks, it's super powerful. So let's take a step back and try to piece together reinforcement learning with human feedback with large language models. Let's start from reinforcement learning. So reinforcement learning, as we know, is a type of machine learning where an agent learns to behave in an environment by trial and error. The agent receives rewards for taking actions, and this leads to for taking actions that lead to desired outcomes, and penalties for not doing so. Over time, the agent optimizes itself and learns to take actions that maximize its reward. The benchmark policy, more mature and stable policy that we still use until today for reinforcement learning is PPO. We can talk about it more later. So how does human feedback plug into this model? Human feedback is actually providing the reward for our system, the reward to the actions of our system. And because human feedback is not scalable, we cannot have annotators annotating everything all the time when we train our model for 50,000 rows of data set. We actually train a reward model to model the human preferences, and then we can use this reward model in place of human feedback. Next step is so you see that the generated text from the LLM goes into the reward to be scaled by the human to get the reward. The reward is usually a scalar from 0 to 5. That's how ChatGPT works. It's a single scalar. So let's say we have the prompt for text generation, the dog, and the LLM outputs the dog ate the cookie. So let's say that for any reason, a reward model gave a number of 4. This is kind of the pipeline. But let's see now where the language model plugs in. The language model is our brain, our agent. It's what calls the actions and also what is optimized. And how are the actions looking here? So the actions are the entire generation of the sentence, or it would be also the entire summarization. It's not token per token prediction. It's the entire generated response. So the large language model sees the prompt, and based on its weights, it outputs, it generates the completion of the prompt. And the reward model, conditioned on human feedback, rewards the model, and we go into this optimization cycle. That's how we try to piece it together to show you guys how it works. So now this is the general picture. Let's go into specifically how this is implemented. So when implementing reinforcement learning from human feedback for LLM training, there are 3 major components. You can see them on your screen. Let's start with the first. Once you have a pre-trained language model, you perform a traditional supervised fine-tuning step using a labeled dataset. At the end of this step, you end up with a trained language model, which is your main model, your base model, and the one you want to train further using RLHF. This step, note that this step is optional, depending on the strength of the pre-trained model. It is best practice to first do supervised fine-tuning, and because you achieve much better performance with the downstream RLHF. Recently, this step is, instead of doing supervised fine-tuning, people are using few-shot prompting. Just note that. So this is the first step. Second step is the rewards model. The main objective here is to use the reward model to mimic the human preferences and be able to then perform RLHF training without the human in the loop. So these are the 3 steps, and we're going to dive mainly into the 2 latter ones. First, though, you should ask, this is a lot of code, probably 3 training steps. So is there code? And yes, there is amazing code implemented from Hugging Face, the TRL library. It comes with good documentation and examples, and this is what me and Juan looked into and actually used in our notebooks. So you can see the same 3 components here: the supervised fine-tuning trainer, the reward trainer, and the PPO trainer. If we go back, they correspond to these 3 steps. They wrap around all of these internal processes, or most of those at least. You will see in the notebooks, and they're quite easy to use. So let's go and check the 2 latter steps, because the first step, supervised fine-tuning, is an exhausted step. It's a bit out of scope from this presentation. But what we have in summary is that after the first step of SFT, we have fine-tuned our original base model on a summarization dataset, which you will see in the notebooks. And so we stand at the point that we have an initial trained large language model, fine-tuned for summarization tasks. We can prompt it with a long text, and it will return a summary. So let's go to the reward model. Let's step into it. The reward model. The underlying goal is to calibrate a model that takes in a sequence of text and returns a scalar reward, which should numerically represent the human performance. The model itself can be another LLM, either fine-tuned or trained from scratch on the preference data. Here, what we used here is an encoder model, BERT, what we used for our case studies. And the size that you need to use for this model is relative to the specific task. The rule of thumb is to have the same amount of transformer layers as the RLHF model. So you have your base model, and you also have this language model that will model the preferences. The bigger the initial language model, the bigger the reward model has to be. There is a relation there. And the intuition behind that is that preference models need to have similar capacity to the language model that they are training, so that they understand the text. They can understand the semantics and the context. So the training data set for the reward model is generating by sampling a lot of prompts from a predefined data set, and the prompts are passed through our fine-tuned language model from the first step to generate multiple responses. So essentially, we end up with a comparison data set. It has a prompt, and it has columns for each of the responses. What it looks like for our case, sorry for the small letters, we're going to use this one. It has a prompt, a chosen summarization, and a rejected summarization. This is a Hugging Face data set. So we will try to model our preference model on to always rank the chosen response better than the rejected one. And so let's go through this. So we have prompts, they come into here, and we feed our language model with prompts, and the language model outputs many responses. The human scorer, annotator, his objective is to rank these responses, not necessarily to score them, but to rank them. And now, after the human annotator ranks them, we have actually we have a data set that we can use for supervised learning. So we are training our reward model based on the prompts and the ranked responses. And Juan is going to show you how this is really done in the notebook, and which we can actually go pretty soon, I would say, in the first notebook, which is good. We have saved some time. So the assumptions we use for this notebook is that we're not doing the fine-tuning step. This we have done for you. It's in the GitHub repo that we will be sharing, and it's also saved on Hugging Face. You can load it from Hugging Face. We are following exactly the method that we described until now. We are using the T5 model, base model, as our language model to be trained, but that's for later, because now for the reward model, we're using the BERT encoder, as I mentioned. The data set I showed you, you will see more with Juan, and you might need to run this on a GPU on Colab. And we are training it only for a few epochs so that it's not computationally intense. So Juan, go for it.
Take it away. Thank you very much,
away.
Pano. I'm going to share my screen now and start seeing the magic. Okay, everybody's going to have a link to these two notebooks. I'm going to show you two notebooks. First is going to be the rewards model, which is in the heart of the RLHF system. This reward model will basically be the judge. It will contain the knowledge, the alignment of the humans. This notebook, we have tried to document it as much as possible. Basically, every single line is being documented so that you understand step by step what is going on. But I'm going to jump through it quickly. First of all, we're going to be using the transformer library to import the auto model for sequence classification. Remember, we're talking about a rewards model. The rewards model needs to take a sentence, needs to take text, and convert it into a number, into a reward. For this reason, we need a kind of model that does this type of task. And for that, we have the encoders. In the transformer world, the encoder will take an input, like a text, and then convert it into an output in the form of numbers. That's why we picked BERT. BERT seems to us like a very manageable code or model that you can run in your computers, even in CPU. And that's why I love the BERT, because it doesn't require you to run this in a GPU. You can run it in CPU to test in case you don't have a GPU access. Or you can do it in Colab with a small GPU. So let's move on. Here we're loading the BERT based on case model as we shared, both the model and the tokenizer. And we will be using a data set from Hugging Face that I will show you right now. The nice thing about this data set is that it comes formatted as a rewards model needs it. It has a prompt, a chosen, and a rejected. The prompt is where the model would start. And then a human, in this case, is actually AI, but a human would come up with a summary that is chosen and another summary that is rejected based on this prompt. We will see that what we feed the rewards model is the chosen and the rejected, not the prompt. But it's important to understand the architecture of the data set. Another thing that is very nice about this particular data set is that we have lots of splits and samples. We used the valid one to train the base model, the valid 2 to train the rewards model, then the train to train the PPO, and the test to test. So basically we had already the homework of the model of the data sets ready. And this is going to be one of the hardest parts when you try to implement a rewards model from scratch, getting the data sets as needed. Let me jump back to the notebooks now. So we load the data set, the tokenizers. I'm going to work with the valid 2 split as I shared before. And that split has 52K samples. I'm going to work on it with 40K samples. And these 40K samples will be split in 2, actually in 3. So we will train the model with less than 40K. It's going to be like 32,000 samples that we will be used for training. After that, we're splitting the data set in the usual train, val, and test, using 80% for the training. We drop, and let me show you here. When I loaded the training, val, and data set, we had the known prompt, chosen, and rejected features in this data set. And for the train, we have the expected 32,000 samples. But we really don't need the prompt. So we are going to drop the prompt and keep only the chosen and the rejected. Since models don't understand words, we have to convert this. And to do that, we're going to create a few more features. They are the input IDs chosen, the attention mask chosen, the input IDs rejected, and the attention mask rejected. Once we do that, it means that we're taking the chosen summary and convert it into numbers, and the rejected summary and convert it into numbers. And then we drop the chosen and rejected features. We don't need words anymore. We only need numbers. So the data set becomes these 4 features: the input ID chosen, attention mask chosen, input IDs rejected, and attention mask rejected. Let's move on, and we're going to prepare the training objects. Basically, we are going to prepare a compute metrics function here that will tell us how the model is behaving. And then we instantiate the LoRa configuration. Remember, we are fine-tuning BERT to be the rewards model. You have 2 options. Option 1 is do a full fine-tuning of BERT. And option 2 is doing a fine-tuning using adapters, in this case, PEFT with LoRa. We chose the second one. We are going to fine-tune the BERT using PEFT and LoRa instead of a full fine-tuning. And here we are basically configuring LoRa. Each one of these parameters, you will find them explained here So if you don't know or don't understand any of the parameters here, you will be able to see a little bit more about them here in the explanation. Once we have set up our LoRa config, now we go for the training arguments of the model. We're about to start the training cycle. And again, we're gonna pass a directory, a folder where the model will be saving checkpoints, and at the end it will save the final model. We're going to be training and doing evaluation, and we're going to be doing that in every epoch. We trained this model for 8 epochs. Again, each one of these training arguments are set up here, explained here. And finally, the trainer for the rewards. Remember that Pano showed you 3 boxes from the TRL library. The middle one was the reward training. This is the one we are using here. And to do that, we're basically passing the arguments that we defined above, the model that we instantiated above, the BERT, the tokenizer, the training and validation datasets, the PEFT config with the LoRa parameters, etc., and the compute metrics that we defined above. And we're going to define a max length of 256. We tried it initially with 512, but the results were not as expected, so we lowered it to 256. Also, if you check about the length of the trainings, the max length was 172. The max token length was 172. So being at 256 is going to be safe. We're not going to be losing any information here. We do the training loop. We're not going to do it right now because it's going to take a few hours. But we're showing you here the schedule of the training. So if you want to go through it step by step, you will see all the results of each one of the epochs here. And we finally save the model in wherever you want to save it. I'm not going to run that step right here, but I am going to load, and you will be able to load the model from this Hugging Face repository. You can load the model here, and when you load it, you will be able to run inference below. We have a results trainer. I will not evaluate it here. You will see the results of the evaluation as well when you run it. And the inference. In the parameters, we will show you how to run inference. You will see all the documentation about the inference that we're performing. We created a score summaries function, which will be the one that returns the rewards. This is the function that eventually will be used in the PPO model to do the actual rewards, or to generate the actual rewards and get them and pass them to the PPO algorithm to fine-tune the policy model. We can run some examples here. For instance, here we have this example, chosen summary and rejected summary. We took them from the data set that I showed you before. When we run this, you will see that the summary, this score summary function throws these 4 numbers. It will show you the chosen score, the rejected score, the chosen logit, and the rejected logit. For the PPO, we will be using the logits. As you can see, the chosen summary is getting us a 0.07 logit, and the rejected summary is throwing a minus 0.0174 logit, which means that the rewards module is picking the right summary for the whole cycle of the PPO and the reinforcement learning. So this is it for the rewards model. When you play with this notebook, you will be able to enter more examples, see more results, run the evaluations, etc. We're going to share with you now the link of this notebook, and you will be taken to break rooms with a partner where you can run this model. You can go from top to bottom. My only recommendation is do not run the training. Skip running this line here because you don't want to wait 4 hours here until this finishes. skip this line. You can run from all the way from this point up, skip the training, skip the saving of the model. You don't need to do that, and continue from this point down. You can load a pre-trained model already, and you can play with it at will. So, Sarah, we're ready for the breaking rooms. Oh, wait, before that, let me share the link where you will find this model. Is going to be pasted in the chat. You can take it from there, download it, and play with it for the next 10 to 15 minutes. So, Sarah is in your hands now.
Thanks, Juan. Yeah, so what we're going to do is we're going to open up the breakout rooms for 15 minutes and let you guys play with this. Thanks all. See you soon.
Hey, Juan, sorry about that.
Yeah, it's fine. Yeah. Welcome, everybody. Welcome, welcome. Where is my friend Pano? That's weird. Pano left? Okay, if at this point you have gone through part or all the first notebook, this notebook was the rewards model notebook. It's a single model that, as I was explaining to Laura a minute ago, is based on an encoder model, encoder-only transformer, because we want to get a number. So this is a classifier model. So and BERT is small enough. So that's why it's good to do this type of project. Sana, do you have a question? Sana, you're muted.
Yes. Hi. Actually, I have a doubt. Like, can you just explain how reward model is work theoretically? How the approach should go?
How the
Which
model
model?
what?
Reward model.
Yeah, and can you repeat the question about the reward model?
So, can you explain how the reward model works?
Sure. So this is I was sharing with another group a minute ago. The reward model, the essence of the reward model is that you will give it a sentence, for instance, in the task of summary improvement of summaries, which is the task we're solving. You give it a sentence, a summary, and the reward model will throw a number saying, let's say, qualifying this summary. If the summary, the reward model thinks that the summary is good, it will give it a high number, let's say 0.7, 1, or 2, depending on the span of outputs that you define. But if the model thinks that the summary is a bad summary, then it will give you a lower number, like a negative number. In the example that we shared a chosen and a rejected summaries. And you can see how for the chosen, the model said, okay, the chosen's logit is 0.7 and the rejected summary is minus 0.6. So basically it gives a qualification, it gives a value, it gives a reward. We take the chosen reward, not the other, but the chosen reward, and we will pass it to the PPO model, and we will see that in the next notebook. Okay, so we're just understanding the rewards model. Now, that's how the rewards model works in general. Why is this special? When you fine-tune the rewards model, this is not just a regular fine-tuning. It's not like, oh, I know how to fine-tune, supervised fine-tuning, and I will do my rewards model with supervised fine-tuning. No, that's not the way the rewards model works. The reward model has a special reward training library because the training of the rewards model is different from the training of or the fine-tuning of a supervised fine-tuning, for instance. And you may ask, how different? Why is it different? Because in the training loop, the loss function is calculated based on the logits of the chosen and of the rejected inputs. In other words, to train the rewards model, you pass it always, the data set is built of the chosen and the rejected, as we saw. In the loop of the training, instead of doing one single forward pass, we do two forward passes. One pass for the chosen, and we get the logit of that. One pass for the rejected, and we get the logit of that. So we have two logits instead of one. What do we do with these two logits? We calculate the loss using a special formula. The special formula is the log sigmoid of the difference of the chosen logit minus the rejected logit. And then you get the loss for the training loop of this model. This is different from what you do in a regular fine-tuning. So that's how it works inside of it. That's what creates this as a special, a different, animal of a model, to put it that way. And again, the only thing it does once it's trained and once you put it inside the RLHF cycle is receive a sentence and spit a number. Good, bad, with a number. 7, very good. 2, good. -1, very bad. That's what it does. And we will see how that couples with the rest in the second notebook. I hope that answers your question. Or anybody else has any other question?
Yes, understood. And can you tell, you were telling we need an encoder model only?
Yeah. For the reward model, you want a base model that will give you a number as a result, right? If you were to use a full transformer encoder decoder that goes encoding sentences and decoding output sentences, no, you want a classification type of model. And BERT is one of those type of models. We also tried with GPT-2 and it worked fine, but BERT was lighter and very good, very strong. The one we're using has like 158 million parameters. You can train it in your own computer, and that's probably why we wanted to use this one. Yeah, Susmit, the bidirectional also helps. Any other comment or question?
Is there any intuition on why this model training process is like this?
Yeah, it makes sense to, in my head, it makes sense to do this training process like this, because what you want from this model is to maximize the distance between chosen and rejected. Okay? And the way to do it, when you look at the formula of the loss of this model, unfortunately, I don't have it here. You will see that they always take the difference between the logit of the chosen, the logit of the reward, or of the rejected. They calculate the log sigmoid, and then they take the negative. And this formula, the concept or the nature of the formula is to always maximize the distance between the one and the other. In this case, the chosen and the rejected. And that's what we want the model to learn. So that's why this works. Now, Jason is asking a very interesting question. As I said, we're using chosen and rejected. And Jason is asking if we could use 3 instead of 2 inputs. My answer is yes. Now, if you want to do it, you cannot use the standard reward training formula that the library of transformers is offering. You will have to build your own, right? But yes, you can customize it. You can build it as long as you understand the essence of it. You can build it however you want. In fact,
I would Juan, I would try maybe to just replace the sigmoid with softmax and see if it works
Exactly.
for all of them. Yeah.
In fact,
But,
in fact, for the multi-class, which is the case of JSON, the softmax is one of the possible solutions to do it, Pano. You're right.
Yeah. Okay, let's go into the next section to see how everything plugs in, and then we can have more questions, and then we can go to the notebook and then back to Q&A. So the 3 steps, again, supervised fine-tuning gives us a trained language model, which plugs into step 3. Step 2, the reward model gives us a trained reward model, also plugging into step 3, where we're going to use reinforcement learning to train the initial model coming from step 1 with using the reward model coming from step 2. You're going to see how this is done. So this is a visually very complex picture. Let's try to break it down. Let's see, first of all, how many models we have in here. We have our initial fine-tuned model. This is our reference model in official terminology. Then this we already created it in step 1. We are reloading it from step 1 in this position, the same model. This is called the policy model. The policy model is different from the reference model because the policy model will be updated from PPO. The reference model will be frozen. No change will happen in the reference model. And you will see why. The policy model, on the other hand, will keep updating through the RL loop. And also we have the reward model, which is also the BERT that you just trained to give us the scalars we need. So let's first see the most important part. So I've tried to make this as easy as possible. Let's see how the policy model, the one to fine-tune with RLHF, so the policy model, how it integrates to our rewards model. So first you take a prompt, you pass it through the policy model, and you generate some text. And then you pass it into the reward model and you generate a scalar. That's the process until here. Prompt, policy generation, scalar. Let's go to look. So we end up with a scalar which is the reward, the human simulated reward. But why do we need the reference model? Why do we need our initial model to be there and generate text? So you need to set some constraints. This is a constraint. Otherwise, the algorithm has proven to generate gibberish. The reason is that if the reference model is not there, the policy model finds a way to trick the reward model to give it high performance without even making sense in what it writes. It writes gibberish. It's not text. It's something else. But it tricks the reward model. This is a problem of reinforcement learning algorithms. They can trick their environment. So what we do, we use the reference model to constrain how much the policy model can be updated. So here, right here, you see this KL divergence. We're actually computing a ratio. It's like regularization, right? We're computing a ratio of the output of the reference model and the output of the policy model. They both have the same prompt. And because the policy model has been updating, it's slightly different than the reference model. So we don't let it go too far. So we generate another scalar from here, and we add them up to build our, we add the scalar from the KL divergence and the scalar from the reward to generate our reward. And now it's, this is how we generate a reward. And now it's pretty straightforward from here. We plug the reward into the PPO trainer, and the PPO trainer executes the optimization loop based on its RL approach. So during the optimization loop, we do the same. We update the policy model, running the loop of steps and epochs with the PPO. And then when we're ready, we choose another prompt. We pass it through the two models, we calculate the reward based on KL and reward model, and we feed it back to the PPO. And this is what you're going to see in this notebook. We're going to use the TRL library. Juan will explain everything, but first, let me know if you have any questions.
Can you repeat why we need the initial model again?
Yeah, so the initial model is there to generate. So the initial model and the tuned model, they are the same model when we begin this process, exactly the same weights. But the initial model stays frozen. Why? It stays frozen so that we compare the generation from the initial model against the generation of the tuned model. This comparison will tell us how far the tuned model has drifted. We don't want it to drift too far. This is the essence of PPO as well. We don't want a model to drift too far because it generates gibberish, and this has been proven, and we could even do it. If we strip off the KL divergence from our code, we actually could prove this.
So is it like trust region kind of scenario?
Yeah, the trust region isn't here, but this is a trust region, an ad hoc trust region implemented specifically for RLHF for large language models.
So isn't there a TRPO model, trust region policy optimization?
Yeah, this is in the PPO algorithm. This is in the blue box here. And it runs on its own. It's completely different. Any more questions or
what kind of challenges did you face during this?
Oh, there are a lot of challenges. From the latest challenge we faced was that our reinforcement learning loop was complaining about the KL divergence. At some points, our tuned model was producing worse answers than our worse responses from our initial model, but the reward was getting bigger. So that was one of the challenges. What else was it? Juan, can you jump in to?
Yeah. So I would say I would say that besides the challenge that Pano was saying, the biggest challenge really was to understand the inners of this process, because I mean you can basically go and connect the libraries and make it work, you know, and it will work, but you are taking a leap of faith just by running something that you don't understand how is working behind the scenes. And for instance, you can have questions like the one Jason asked. Wait, can I do it with 3 variables instead of 2? If you understand the inners, you will be able to come up with ideas and create your own solutions. But if you just stay at the abstraction that the Hugging Face libraries give you, you are controlled by the what is the word? By the way that the libraries are built, by the idiosyncrasy of the libraries, you know? So that was the biggest challenge. Other than that, of course, this is a toy project, an academic project, and still we had issues with the training loops, the delays, you know, the collab crashing. But when you take this to the real world, you have to face larger data sets that will take longer, and that you may have to clean and to adjust and to fine tune. So that's going to be, you know, in production, the real challenge of this.
Yeah, great.
Any other question?
I saw a hand raised.
Yes.
Yeah,
just 1 minute.
We have to jump in 2 minutes to the notebook so that we can go
just
through it.
one question is, did you try it without using the TRL library?
Yeah.
Or
Yeah, I did that initially, and one of the notebooks that we developed first was without the TRL library, both for the fine tune. The only part, and let me be clear here. Again, there are three components. You have the base model that you want to enhance, align. You have the rewards model, and you have the PPO. The PPO part of it, if you look at the articles, at the papers that propose and describe PPO, are a lot of math. And I particularly didn't want to get into that detail, so I did use always the library of the PPO. But for the other two parts, we developed from scratch. For this presentation here, we are using the two libraries of the TRL, but in our understanding, in the process of creating this for you all, we went from scratch all the way to the libraries to be able to answer your questions. But if you ask me the formula of the PPO, I will say, I have no idea. I don't want to learn it. And not only because it's complex, it will take me some time, but also because it's changing. There is new research around this technology, and that's going to change. So it's going to be another deep learning that I will leave to the PhDs.
Okay.
But let me jump to the second notebook. I'm going to be sharing screen now. Thank you for the questions, amazing questions.
Yeah.
In this notebook, we have 4 things happening, and I'm going to jump to them quickly. Of course, we get the libraries, etc. The first part is we're going to instantiate the rewards model that we built in the first notebook. Basically, I call it here. I am instantiating it. I bring the same summary, score summaries function that we created in the first notebook. So you are already familiar with this one. Nothing to surprise you here. To make sure that things are working, I am running some examples here again, just to make sure for sanity sake. That is the first part. That was fast. The second part, as you know, we are trying to align a model to human criteria, to human preferences, using human feedback. We chose T5 as the model that we wanted to align. We took a T5 model, we fine-tuned it. That's a regular supervised fine-tuning process with one of the splits of the data set that we showed you. And that is going to be the model that we will align. So here I am basically instantiating the fine-tuned model, the T5, that is going to be aligned. I bring it here. I test it to make sure that it is working fine. You always have to test. And then I will have model for fine-tuning. And for that, we will use again LoRa. We could use full fine-tuning, and you can do it, but LoRa has proven to be very good. So why not use it? We instantiate LoRa, and here we get the policy PEFT model parameters that we will train. Next, and this is the second magic here, attention to this. I have a rewards model instantiated, ready to play. I have a T5 model that is being fine-tuned already and that we want to improve using human preferences. As Pano was saying, we take that model and we're going to have 2 copies of it. One copy is going to be frozen and one copy is going to be modified. Here, using the auto model for sequence-to-sequence LM with value head library, we take the T5 model ready with PEFT to get the policy model, the PPO model, okay? here, remember the graph that Pano was showing, two models that we're going to target? This is one of these. This is the one that is going to be modified, the PPO model. And then we create the reference model. For that, we take the policy model and we apply the create reference model, which is a library provided by RTL, to create a reference model. You can create this manually, but you know that's a simple for loop and a couple of things. So why not use this create reference model function? Now you have this model, which is going to be fine-tuned with the human preference, and this model, which is going to be the reference. Both models have the same information at this point, but this one is going to be fine-tuned. The only thing that I want to show you here, and it's going to be a very quick and technical aspect that you don't have to learn necessarily, is that this model has an extra head called the value head. And the value head is important in the whole process, but we can discuss that later. Just know that even though I'm taking the T5 fine-tune and creating two models, the one that we will be changing is slightly different. It has an additional head that will help us in the fine-tuning process. Let's move on. We get the data set. It's basically the same processes that we ran before, so I'm going to skip this quickly. We have making sure that we have the inputs and the responses. And then we have here the data set. Let me jump. We have a data collation function. Everything is explained. Whatever you don't understand, don't worry. In these notebooks, we took special attention in explaining every single line of code. So you will be able to take this and understand every single thing. So let's move on. We take some hyperparameters. Here, we are going to define the parameters that we will use when doing inference. We use temperature. You know, all of us know about the parameters that you can use to generate inference in an LLM model. You can fine-tune them here. And in this case, we just do a fine-tuning for 100 steps, very small. We have the PPO configuration where we're passing the policy model, the learning rate, the epochs, the mini batch size, and the batch size. And finally, we create our PPO trainer class. This is where things are going to happen. Aquí, Maggie. I'm sorry.
Guys, reach out to the chat to find the notebooks, and you can open them if you want.
Okay, so going back here, the PPO trainer, we have the PPO model, the reference model, the policy tokenizers, the training data set, and the collator. So basically, we're instantiating here the PPO trainer, and we are going to train it here. And this is where the big magic happens. This is the training loop. In the training loop, we are going to go through our data set. Basically, we convert it into tensors. The prompts that we are receiving are converted into tensors. And for each tensor, meaning for each one of the summaries that we will be using on the training on each step, we will get the inference from the policy model. Here you have it. The policy model generates the summary, and the summary is converted into a tensor. And we batch that. We pass a few of them, 16, 32, whatever you define, to a batch with all the responses from the policy model, from the model that we are affecting, okay? We take this information and we now pass each one of these through the rewards model. Remember that we created the score summary. The score summary is going to use the rewards model to get a score for each one of the components of this batch that we passed already through the policy. Once we finish doing all this inference with or getting qualifications or scores better from the rewards model for each one of the components of the batch, we pass it to the PPO trainer in a single step. We pass the prompt tensor, we pass the summary tensors, which is what we got here, and we pass the reward tensor. Look how we pass the 3 components, and then the PPO will do its magic, apply KL divergency, and then calculate the next step on the PPO policy model, do the fine-tuning step in the PPO policy model, and return. And we repeat that for 100 steps. We get, after each step, we get some statistics that we show here. And you will see here the log of the training. You will see how we started with a return of 0.38, and you want this to go up. So we go through the 100 steps here. And from 0.38, we end up with 0.56. Remember, this is just 100 steps. You want to run this for a few thousand steps. So you actually will see the big change in the model happening. After we run this, we save the model, don't run this. We run inference. For that, you can run this, loading the weights already pre-computed for you. And you can test the summaries using this generate summary and see how it qualifies. Then you have the conclusions, and that's basically it. So to recap, we are loading the rewards model. We are running the base model, which is a T5. We are splitting that model into, one is going to be the policy model, one is going to be the frozen model that we will use as reference. And then finally, we build the PPO training, loop through it 100 times. And for each iteration, we take the data set, we ask the policy model to give us inference. We pass those inference to the rewards model. The rewards model returns scores, and then we give that to the PPO to do the adjustments in the policy model. That's basically it. If at this point we want to invite you all to run to the break room again. Pano, you want to say something?
But are we going to breakout rooms, or is it too late to go to breakout
I think
rooms?
that we can go to, oh yeah, it's a little bit too late. Yeah, maybe we go to question and answer because we have 11 minutes to go. So if there are questions, let's it's the moment.
What do people, Greg, what do you think? Should we go to breakout rooms or complete the presentation? We have one more slides and go to questions.
Greg isn't here. I'm wondering how much more information do you have right now?
Only one slide about limitations, bias, and stuff like that.
Let's go to the slide, and then let's go to question and answers.
Right. It might be more useful to do that.
Yeah. Okay. So talking a bit about limitations and variations. RLHF is sample inefficient. This is because of the PPO. The PPO is a trial and error algorithm, which means that it needs to try a lot of times, and this means that it needs a lot of samples. The second challenge is that human annotators can disagree or can even induce bias, or due to the disagreement, big differences in their annotating. And if you don't have a ground truth, your algorithm gives wrong results, gives biased results. So also when deploying a system using RLHF, gathering human preference data is very expensive. And the performance, of course, of the algorithm is only as good as the quality of the human annotations. Generating human annotations and well-written human text, actually, if you want to directly get the human text, is also very costly. So luckily, the reward model doesn't need much to train with. It needs something like 50,000 samples. But to produce them, it's expensive. And currently, there only exists one large-scale data set from Anthropic for human preference data set, right? With human preferences. Only one from Anthropic and a couple of smaller ones from OpenAI. Now, these are the limitations. What other forms does we gave you the traditional one and the most difficult one, to be honest. The other variations of RLHF that we might explore, probably explore in the future, is RLAIF, which you take the human completely out of the loop. You use AI to produce your rewards. This can happen in more than one ways. That's for a next discussion. Now, recently, there is a DPO method developed by Stanford. This takes out the PPO method. and it's very interesting, but it doesn't have much results, and it's only being tested in small models, smaller than 6B. Finally, we want to apply Rouge to evaluate our summarization, because we didn't manage to do this for this section. So that is it. Thank you so much for going through this complex algorithm with us, and we are open to questions.
Yeah, we're trying to teach you here, or to show you here, what took us at least 2 weeks to understand. And still there are many questions. So don't feel bad if you are still in the nebulous trying to understand what's going on. Pano, are you sharing your screen?
No, but accidentally I shut it off. Please go on.
No, that's fine.
Okay.
Yeah, so if you still have a lot of questions, that is normal. As I said, it's been a long process to get here. If you have any question, you can throw it here, or you can contact us by LinkedIn with questions, and we will be more than happy to answer them. So this is it. Let's go for questions, or let's wrap it up.
So any specific reason why you used a T5 model for the policy?
Yes. By the same reason that we picked BERT, because number one, we needed a sequence-to-sequence model. Number two, T5 has a variety of sizes, and it is a recognized model. So we pick one small size. I don't remember how many parameters is the one that we picked, but it was also a model that any of you can train in a CPU. So to build the labs, one criteria that we try to keep in mind is that we want you to go step by step in these notebooks and be able to do it in your own computer. You don't need a GPU to do this. You can run it in your CPU and it will work. So that's why one of the criteria to pick the models was, let's make it fit in a CPU so that the participants can learn about it by doing it. But again, for production size, for production level, you may want to explore more robust models. Again, that will bring their respective complexities, empowering process, etc. Any other question?
Yeah, I have a quick recognition and then a quick question, Juan. So first recognition is to you and Pano. These notebooks are some of the best notebooks I've ever seen for almost anything. Like, they're incredible. And I do not take it for granted. I've seen notebooks on RLHF before that, like, thrown together. I have no idea what's happening. These notebooks, I understand each step. That's just awesome. Yeah, my question was, so thank you for that work. My question was about the KL prediction shift penalty. So, you know, so what we want to do is we want to modify the weights according to the human feedback that we've been given, but we don't want to modify those weights too dramatically or we get gibberish. So that ratio that we're talking about for the KL prediction shift penalty, is that trial and error? Do you try a run where you have a higher ratio, or do you try a run where you have a lower ratio, or is there actually like a deterministic way to determine how big that ratio should be, how much you should modify the weights?
What, Pano, you want to take it, or I would say that it's deterministic, since it comes from a math formula, right? So and that deterministic feature comes from the fact that you are comparing the new model with a base model, and you're always keeping the base model. That's why you have frozen the reference model. So you are always aligned and in tune and within reach of the base model. This will guarantee you, based on the deterministic formula, that you will not do crazy jumps.
And it's like a regularization step. So the more this ratio increases, then the more you constrain your weights. And I think the model learns to respond to that. So it learns to not drift far, or else it will not get a big reward because of this minus in front of here, and then it will it will not, its objective is maximization of reward. So yeah,
Awesome.
very nice question, actually, Jason.
Yeah, so I want to kind of like wrap this up a little bit. Juan, Pano, thank you so much. Everybody give a round of applause. That was absolutely phenomenal. Thank you. And what we'll do is we'll just take a few minutes and I'll send out some feedback forms. And so if you can please take a minute to fill those out, that's how we are able to improve your guys' learning experience and make sure that every one of these sessions is something that is of great value. So we do listen to these. Please jot down anything you need. You can make them anonymous and we'll go from there.
Where is music when you need it by Greg? You're muted, I think, Ali. Or I couldn't hear you.
Yeah. Where is music? So let me get that going.
Yeah, let's.
Yeah, we didn't prepare for the music, me and Juan.
Oh, you're fine. Let's see if we can get something.
That has to go in the forms.
Please click that link and complete that feedback form for us. Sana, Pano, can you share with Sana your LinkedIn?
Yeah. Nice. Here's Sana and everyone else. Feel free to reach out to us. Me and Juan are probably going to keep building and maybe we'll come back with another workshop. Good idea would be to compare, Juan, RLHF with RLAIF with RLHF.
Yep, let's do that.
Awesome. So with that, we'll wrap it up. Thank you all so much and we'll see you on the next one.
Thank you, everybody. Have a great rest of the day.